Hello and welcome to our webinar today, the fiber weave effect and glass weave skew. I'm the host, Bill Hargan, and I'm the founder of a company by the name of Z0, and we make stack-up design software, and we are a partner with Siemens EDA. Let's jump right in. We've got a lot to cover. Here's the agenda for the fiber weave effect and glass weave skew. In the first section, we'll be defining differential skew, and then we'll be talking about the glass weave skew problem specifically. In the third section, we'll discuss who cares, and finally, we'll talk about some next steps. I was fortunate in 2016 at several years at DesignCon, I think 3 years in a row, I presented on glass weave skew, and in 2016, Dr. Eric Bogatin and some of his University of Colorado students presented with me, and we got a Best Paper award. I've seen 5 types of people as it relates to glass weave skew. The first group would be those who don't care about it and aren't doing super high speed design. And to that group, welcome to the webinar. You can learn a few things. Second group would be a pretty big group, I believe, which is those who don't care about it, don't fully understand it, but probably should care about it. To that group, I would give the same advice that I gave to my son when we went cycling last week, and I was able to talk him into getting a helmet on, 22-year-old son. And third group, those who overcomplicate the subject. These are the people that uh, try to calculate worst case skew, which you can do, but it doesn't make sense to know what the worst case skew could be when, as we'll discuss later, skew is really based on probabilities in manufacturing rather than something that's deterministic that you can identify with an equation. The fourth group would be those who care about it, but don't have a handle on the different mitigation alternatives and their costs. And I think all of these groups, by the way, will get quite a bit out of this webinar. This is part one of a 2-part series, by the way. We'll be doing another one in a month. And I want to bring everybody to this point to where all 4 of those groups have a good handle on the risks, the mitigation alternatives, and the costs, and perhaps some are already there. Way back when I was getting started in this space, which would have been in the PCI days where speeds were just 33 megahertz. Speeds were fairly slow, really slow by today's standards. Layer counts were low, decays were high, loss tangents were high. Design margins were pretty wide, and copper roughness didn't matter, glass weave styles didn't matter. Of course, that weighed less, and we called dielectrics FR4, and their properties didn't matter very much. I'm showing over on the right kind of the exponential curve of the last 20 or so years. You can see a very clear exponential trajectory. The vertical axis is gigabits per second, and the horizontal is the year. But you can see a pretty clear trajectory of PCI Express with these green dots going from under 5 gigabits per second to 64 gigabits per second for PCI Express 6. And you can see similar trajectories for the USB standard and also for Ethernet. The bottom line or the takeaway here is you can't design today like you were designing 5 years ago. And the reason is the physical world is doing things to your signals and your signal integrity that didn't used to be issues. And PCI Express today is 500 times faster than it was when I was just getting started in this space. So things have changed dramatically in terms of what you need to worry about. In fact, I highlighted this point in the introduction to a chapter that I wrote for the Printed Circuits Handbook, and chapter 20 is electrical and mechanical design parameters. And what I said was everything in the process of building a printed circuit board, or PCB, works against signal quality. This is why we spend so much time with signal integrity. The electrical world and the physical world are fighting against each other. And as electrical engineers and PCB designers, we need to understand basically the enemy that's fighting against good signal quality. So the more you can know about the manufacturing details that go into a PCB, the better off you'll be as uh, designs continue to increase in speed. Let's define what differential skew is, what we mean by differential skew. And I'll start with a zero skew example. And here we've got a perfectly aligned, well, not perfectly aligned, but pretty well aligned differential pair. And skew is measured in picoseconds, as the slide says. And in a later slide, we'll go into how this signal would look if we introduce some differential skew. I suppose that most people watching this webinar are fairly familiar with skew. It's been an issue that we've talked about for at least, 25, 27 years I've been involved in high-speed design. But I want to talk about some of the different sources of skew, including glass weave skew, so we can put glass weave skew in the context of the other types of skew that people might be familiar with. So it can come from three places, possibly more, but these three for sure. Signal misalignment coming out of the transmitter due to length mismatches in the IC packages, but most of that's under control. Today's ICs are able to maintain alignment at the package level to as little as a picosecond. Different PCB routing lengths. For years, PCB layout tools have been able to match lengths to as close as a picosecond. So that's probably not going to be an issue on your designs. But differences can emerge in flight times on the two paths due to what we call glass weave skew. And that's what we'll be talking more about going forward here. It's interesting that the range can be from 10 to 100 picoseconds, quite a bit more than what you'll see from the other sources, and we'll talk about why that is. Here's another differential example simulated with hyperlinks. The blue waveform is showing 40 picoseconds of skew. That's actually not a lot of skew, and you can probably see why a receiver would get confused by the additional delay in the blue waveform. And if you look down at the bottom, I'm posing a question that we'll actually address in a later slide. But first, since we're talking about glass weave skew specifically, let's talk a little bit about how glass laminates and prepregs are made. Glass fabric for PCB laminates are made just like any fabric would be woven in the textile industry, but the yarn used and the weaving characteristics follow IPC guidelines. The top image here, I'll show more images as I kind of roll this out. The top image here shows a good old-fashioned loom. All the loom characteristics here have been around for hundreds of years, but today the equipment that weaves glass runs at super high speeds. The filling yarn in the cross direction is shot through with these automated machines with a high-speed air jet. And if you go into a glass plant or a weaver, as they're sometimes called, um, you'd think you were in a room with 1,000 sewing machines running as the looms do their work, and they make you wear earplugs. It's fairly loud, actually. Um, the other image that I just showed here uh, shows how we refer to the yarn running in the machine direction, left to right, in the loom, and we call that the weave. And then in the cross direction, we refer to that as the fill. But actually, there's several terms that I've introduced here that are basically synonyms for the same thing: machine direction, weave direction, fill direction, cross direction. Those are all synonymous, and the glass comes off the line and rolls, where it's then ported off to be uh, impregnated with resin, making prepreg, and some of that prepreg will later be used to make cores, and the rest of it will be left in roll form once it's been impregnated as rolls of prepreg. Um, in the bottom view here, you can see the weave and fill directions just like above, but note that there are a number of other terms for both of these uh, directions for the yarn. So the machine direction is going left to right. That's known as the weave, sometimes occasionally the warp. Some people call it the grain direction, kind of an analogy to wood, and it's also called the strong direction. The cross direction um, is known as the fill. I primarily call it the fill. Um, I sometimes call it the weft, and I have never called it the woof. I don't know where that came from, but if you know, please let me know. When laminates are made, as I mentioned on the previous slide, um, resin impregnated prepreg rolls with glass reinforcement are pressed and cured between copper foils to make cores. Cores are then cut into sheets, which are ultimately cut into panels. And you can see here this rectangle that I've shown cut away from a roll. This is the roll going left to right. And then I've got 36 inches on the cross direction, and then 48 inches in the machine direction. And then that would be a sheet, 48 by 36, common dimension. There are you can get other sizes, but that's the most common. And the most common panel size, although you can get many sizes, but the most common is 18 by 24. And you might ask, why do I say 18 by 24? Well, the convention is to always list the grain direction second. And so you would say that this sheet is a 36 by 48 sheet, and then there'd be a G in there for the grain direction. In North America, where I live, we've run this orientation for many years. Some large North America fabricators have shifted to the long dimension uh, here being parallel to the fill. So this would be the long direction, and that's how it's done in Asia universally. In Europe, actually, they also run, as far as I know, um, what I would call short grain, which is the short part of a sheet running in the machine direction. In Asia, just to make things interesting for everyone, the dimensions are flipped relative to the historic conventions in North America. Rolls are typically 48 inches wide in the vertical here, and sheets are 36 inches in the machine direction. I mention this because if you're doing prototypes on one side of the pond and volume on the other side, this might be something for you to consider if you're signaling at high speeds. Square glass, which I'll talk about a little bit more in the second webinar, helps with this issue. On the next slide, we'll discuss what causes glass weave skew, something known as the fiber weave effect. But I wanted to point out before we jump off of this slide that some larger North American fabricators, TTM is one example, have adopted this short grain approach, as some of us would call it, but which is the grain direction along the short dimension of a sheet. And they've done that so that on both sides of the Pacific, they'll be ordering the same materials. Let's go into discussing the details of the fiber weave effect. Over here on the right, I'm showing two halves of a diff pair, the positive side, negative side. The positive side is positioned primarily over a weave bundle, a glass bundle. The negative half of the diff pair is primarily over resin. And so you can see that over here as if we took the cross section right here. Um, the negative side is primarily over resin, and then the positive side is primarily over glass. Glass and resin have significantly different dielectric constants, and typical glass numbers, dk, E sub r, or dk, same thing for our purposes. Around 7, and you'll see people use different numbers. Some use 6.8, some use 7.1, some use 7.0. I rounded off to 7, versus in the range of 3, dk of 3 for resin. And it's going to depend on the resin system what the actual dk is. And there are also different kinds of glass, but we'll be discussing that in part 2 of the webinar series. Signals travel faster when the dk is lower. And so a signal, and you can see the relationship over here, that the velocity of propagation, inversely proportional to the delay, is also inversely proportional to the dk. So a signal routed over a glass bundle is going to travel more slowly due to the higher effective dk. And so this one is going to propagate more slowly than this one. And that's what we refer to as the fiber weave effect. And this is what causes glass weave skew. So we've married the two concepts of fiber weave effect, which a lot of people have heard of, and glass weave skew with this slide. The fiber weave effect is a difficult beast to track. What's the chance, for example, that one line in a pair will see a different dielectric constant than the other? Here I'm showing 3 different glass styles with the same differential pair running across all 3. And you might be able to see that there are slightly different microenvironments, as I call them, around the blue trace primarily, but really both halves of the diff pair as you go down the track. I should point out that the worst case scenario here is when the differential pair is routed to exactly 50% of the glass pitch. And I'll talk more about that in the second webinar, and also in a white paper that I wrote that I'll provide a link to at the end of this webinar. So the fiber weave effect, which causes glass weave skew, as we mentioned in the previous slide, is a real problem, but it's hard to characterize because it's statistical in nature. It depends on glass pitch, differential trace pitch, the glass weave, the line length, fabric and resin decays, and the chance alignment of the glass bundles under the 2 traces, under the 2 lines. Let's address the who cares topic that I brought up earlier in the agenda slide, skew tolerance. I've seen a couple of different rules for skew tolerance used in the industry. Lee Ritchie has talked a number of times. He tends to use 25% or 1/4 of a unit interval before signal quality degrades and intersymbol interference occurs. And it's conceptually logical if you think of a unit interval and a bit. If you take 25% of that and you've got 25% skew, the chance of intersymbol interference is pretty high. If you want a more conservative approach, Eric Bogatin in his book, Signal and Power Integrity Simplified, uses 20% of the user unit interval. And a lot of high-speed serial links will specify that for a line-to-line skew tolerance. You can use either. I don't have a strong preference. You could make a good argument that the more conservative approach is better. 20% of the unit interval, if you want to do a calculation, you take 20% times 1,000, divide it by the data rate in gigabits per second, and you get the skew tolerance in picoseconds. I've listed some quarter unit interval numbers over here on the right, and about a year ago, I did a poll. I think I had about 80 people respond, and as to what their fastest signaling speeds were. And 50%, I'm going to round the numbers off, 50% said that they were doing their fastest signals were between 28 and 112 gigabits per second. Another 30% said 16 to 28 gigabits per second. And so what you have is about 80% are saying that their skew tolerance using the 20% unit interval rule would 20% could only tolerate 12.5 picoseconds. So let's start looking in the next slide at how does this play out in terms of how might it look in an actual eye pattern. Let's demonstrate this with a PCI Express, for example, at 16 gigabits per second. As you can see from the slide, I'm showing three different PCI Express generations, PCI Express 3, 4, and 5. We'll concentrate on PCI Express 4 at 8 gigahertz or 16 gigabits per second with a quarter unit interval skew tolerance of 16 picoseconds. And I simulated this with Hyperlink's LineSim. I created just a basic differential example, 15 inches long. And for one case, I had 0 skew, which this would be 0 picoseconds of skew. And then for the second case, I introduced 16 picoseconds of skew. So here's the 16 or the 0 skew example, and you can see that you've got some bits barely encroaching on the eye mask. You might want to use a lower loss material. You might want to shorten the run length. I wanted to create something that was right on the edge though, and so that's what I did here. And then with 16 picoseconds of skew, right at the 25% unit interval limit, you can see a lot of bits encroaching on the eye mask. So this is a very basic example. It shows how glass weave skew can impact an eye pattern. The problem with this is not just that you're encroaching on an eye pattern. This might in fact work with your prototypes. So you build a prototype and this problem doesn't show itself. So you think everything's great. You go ahead and go to volume manufacturing. The problem with glass weave skew is that the only symptom of it is going to be field failure because it's a statistical phenomena. It comes down to when the differential signals are aligned with the glass and resin in such a way to cause this problem. And so it's going to have a defect rate associated with it. And even if you haven't run into this before, I'll use the quote. I heard this from Todd Westerhoff. He probably heard it from someone else, Todd Westerhoff at Siemens. Nothing matters until it does. And I've read that from other people, but I originally heard it from him. And glass weave skew doesn't matter to you until it bites you and you're wondering what happened when you're getting field failures. And It's just like I told my son with the cycling helmet. Um, you don't need a helmet until you need it. And fortunately, he listened to me.
I'm going to provide an example that goes with the PCI Express 4 slide that I showed previously. Before I do that, though, I wanted to point out you can download the zPlanner Enterprise evaluation software. We're providing the link for you. And there's a whole section in there on Glassweave Skew where you could learn quite a bit as a follow-up to the webinar. If I click into the tutorial, you can see it's pretty well explained and illustrated, and it's going to parallel the demo that I'm going to do right now. So this is this is again zPlanner Enterprise. I'm using an open source example design that includes PCI Express 4 signaling on on layers 1 and 3. And what I noticed when I started playing with this design is they've got a lower loss material on the outer layers, and then a somewhat higher loss, less expensive material on the inner layers. You can't always do that, but I believe they probably did their homework and figured they could do this. Some things I noticed: they use dual ply glass. That's good. That's a good weapon to mitigate glass weave skew. They're using 1067 glass, which is a pretty good glass to use, and I'll discuss why. 100 ohms, looks good. I'm looking at a 100 ohm impedance group. There's several other impedance groups that I could look at in this design, both single-ended and differential. But we'll look at the 100 ohm signals initially. So I'm at 8 gigahertz. Recall that that was the frequency for PCI Express 4. And initially, I'm just going to turn on differential pitch fields, and it shows the weave pitch and the fill pitch. This is calculated from the type of glass that's used, and zPlanner knows all about the glass. I'm also going to turn on glass weave skew settings. So when I open this dialog, I'm going to turn off differential pitch. And what we'll discuss both in the tutorial that I pointed out to you and in the next webinar is why the differential pitch for the signal and the pitch for the underlying weave, the glass, matter. How those correlate to each other matters in terms of controlling glass weave skew. But I'm going to turn off those fields for now, and I'm going to switch to frequency dependent fields, and you'll see some numbers that correlate to one of our previous slides. So I've got 8 gigahertz, 16 gigabits per second for PCI Express 4, a calculated unit interval, and then a 25% skew tolerance. So this is all at your fingertips within the software. If you go down to one of the other layers, like layer 5, you can see it's at a lower frequency, 2.4 gigahertz in this case, and higher loss material is being used. There's the higher DF values, and there's the unit interval, much wider unit interval, 208 picoseconds, and then a 52 picosecond, 25% skew tolerance. That's it. I know that was quick, but hopefully it made sense.
That's going to do it for the main part of the webinar. And you can also go, if you want to get more information on glass weave skew, you can go and play with the glass weave skew software tutorial. And here's the link. And you can go through a full 60-minute design tutorial covering glass weave skew and using the zPlanner software.